So we're gonna, I need everyone to be quiet while I am talking. Okay. So we're going to go through each of the scientists that are noted as being responsible for these discoveries.
Can I take Isaac first?
You can have him.
Bro, are you even ready?
Anyways, so we're going to explore that and see how the current model of the atom looks. So we started talking about a guy named J.J. Thomson who used cathode rays, which I forgot to do that, but since a bunch of people are gone, we'll have to do it Monday. You'll have to remind me. Okay? And so what Thomson discovered with his experiments was that that tube or that beam of light in the cathode ray was made up of charged particles. Okay? So what he did, and if we look at page 316, we can see the setup of his experiment there. So he had two metal plates. So he had the tube, two metal plates, one on each side of it. One was negatively charged and one was positively charged because it was connected to a battery, okay, a power source. And when he turned it on then, so that it did have those charges, he found that the ray was bending one way, which was towards the, which plate?
Negative.
Towards which plate?
Positive.
The positive one. Okay. What do we know about charges of things?
Positive.
Opposites will
Attract.
attract. So, because it was bending towards the positive plate, what does that tell us about the charge of the particles that made up that beam of light?
Negative.
That they were negative. So he concluded that they were negatively charged. Okay? So determined that the rays were made of particles that had mass. The mass of the particles was smaller than the atoms. And so his discovery were electrons, which are particles that make up atoms that have a negative charge to them. And because these atoms had particles that were had a negative charge to them, he concluded that there must also be a positively charged particle that make up atoms. You see that, Sydney?
Can I just don't know if it's like the answer for two Thompson.
My brain's too slow for this.
Might help if we go to the next part. So the atomic model that Thomson came up with, he called it the plum pudding model. Which does not necessarily make sense to you guys, because you guys don't know what plum pudding is, do you?
It's a pudding made out of plum.
pudding.
Okay? It was something that was common at that time. It's not something that is common now. And so even though he called it the plum pudding model, I like to call it the chocolate chip cookie model.
That sounds better.
Yeah, it's better.
Okay? So what he said, what he thought is that an atom then was made up of a ball of positive charge that had these negative charges embedded throughout it. There's a picture of what he thought it looked like on page 317. Okay, so this ball of positive charge with negative charges embedded throughout it. And so if we're just looking at a picture of it, you can see how it resembles a chocolate chip cookie. Okay, so the cookie itself being the positive charged particles of it, and then the chocolate chips being the negative charged particles. Okay, makes more sense when we look at it in that way, right?
Charged ball with a negatively charged what?
positively charged ball or sphere with negatively charged particles embedded throughout.
Yes.
And like I said, I like to say it's a chocolate chip cookie because that, like, you guys can relate to that more than you can plum pudding model, right?
Boom. Did we get chocolate chip?
Nope. All right, our next scientist. I need everyone to stop talking. Our next scientist is a guy named Ernest Rutherford. He was a student of J.J. Thomson's. And because he was a student, he knew a lot of that information, right? And so he wanted to test Thomson's theory to see if he was correct in his assumptions. So if we look at page 318, those show the predicted results of what Rutherford's experiment would be. And so you might hear it referred to as Rutherford's gold foil experiment. Okay. And so basically he shot a beam of alpha particles through a sheet of gold foil. And what he thought was going to happen based on Thomson's model of the positively charged sphere with negative charges embedded throughout it. What he thought was going to happen was that the beam of light, those alpha particles, were going to just shine right through. And so if we look at this is what's on figure 6. So these being the particles of gold that made up this gold foil, he thought they were just going to go straight through. And those alpha particles were going to go straight through because of the positively charged and the negatively charged was kind of evenly distributed. It was just going to pass straight through with no problem. And so he was expecting, so he had this screen here that would detect, it's kind of like film from old cameras. You guys ever seen one of those before where you actually put film into a camera and you take the pictures and you get like 24 pictures and then you send that film off to get developed? Have you ever seen that before?
Like the camera things, like where you take a
Yeah.
picture of it and then
Yeah.
you take it out and wave it around and it prints it.
No, that's a Polaroid.
Oh, Lord, those are fire.
Not talking about that. I'm talking about actual film. Anyways, it detects those alpha particles. So this screen here, if these alpha particles hit it, they were going to detect that. And it would make a mark on that screen. And so this is what they were expecting, was just one single spot here to be on the film when they got done with it. Okay? So, shot a beam of alpha particles through a sheet of gold. What they actually found, okay, so page 319 has what actually happened then, okay, surprising results, okay, what they predicted was going to happen did not happen, okay, most of the alpha beam particles did move straight through the foil. So, for the most part, it did do what they thought it was going to do. But some of those particles were deflected off at different angles. And you can see that in figure 7. Okay? So, this is what they actually found then. So, they shot it here. And most of them went through, but some bounced off at really weird angles. And we can kind of see that here. Okay? Different angles, not ever the same angle, but at different angles. Sometimes they bounced almost straight back. Sometimes they were slightly deflected. Some of them like a 90-degree angle, sometimes greater, sometimes less. Okay? And because of that, they advanced the model of the atom. It looked different. So Rutherford's model of the atom looked different than that what Thomson's did. So because the majority of the beams pass straight through, he concluded that the atom is made up of mostly empty space. Which is kind of what Democritus and Dalton said, right? He said that where the particles were deflected, whether it was a very small deflection or a very large one, okay, they deflected because they hit a positive mass. And so, small volume, it was very, very small. However, the mass was very, very large. And so, Rutherford came up with the idea that an atom has a nucleus, which contains most of the atom's mass and where the positive charge of it is. And so, they called those positively charged particles protons. Protons. So, protons are found in the nucleus of an atom. They make up a large portion of the mass, and they are positively charged. And then he also came up with the idea that these electrons, the negatively charged particles, occupy that empty space that is outside of the nucleus. Which led to the model of the atom to now look like this at this point. It's not what our current model looks like, but this is what Rutherford came up with after he did his experiment. So we have this nucleus made up of protons that is positively charged. The majority of the mass is found here. And then these electrons, the negative charges, are in the space that is surrounding the nucleus.
What's our model look like now?
We'll get there. A guy named James Chadwick also contributed to the model of the atom. And he was a colleague of Rutherford. And his contribution is the discovery of neutrons. And I guess I don't really know how he did that. Doesn't really talk about that, I guess. Okay. And neutrons are the other subatomic particle found that make up atoms. It's found in the nucleus of an atom, and it is a neutral particle, which means what? Neutral means there's no charge to it, right? So now we have protons that are positively charged. We have electrons that are negatively charged, and now we have neutrons that are neutral. They have no charge on them. Okay? So what is their function? Well, they're found in the nucleus of the atom as well, and they are roughly the same size and mass of a proton, and so they add to the mass of our atoms. All right. Another scientist named Niels Bohr came up with some ideas about the atomic model as well, because several of Rutherford's observations could not be explained by the models that were present at the time. So he was studying that certain elements gave off specific colors of light when they were heated. And each color of light had specific amounts of energy. Who in here likes fireworks? What color of firework is your favorite?
The one that
Every
goes-
single color.
Any of them that make the biggest. Any of them that go
Black.
I just like the noise.
Oh my gosh! I like
Black
that.
line.
Do you have a question or are you just raising your hand because everybody else is?
Yeah.
We're talking about fireworks.
Fireworks?
Yeah.
Oh my gosh.
Okay, so anybody know how fireworks work?
Yeah, you
The
light
light
it,
is
and
the-
there's a bunch of like
And then-
gunpowder and stuff in there. Just,
I don't know.
So
I just
why-
like to make the-
bam!
There's a lot that goes into it, but the main thing that I want to talk about is the color of the fireworks. Okay.
There's like a specific type
I'll
of-
tell you if you quit talking, or we'll just move on. Okay. The different colors are because of the different chemical compounds that are inside of that artillery shell. So if it's red, it's because it has, I believe, strontium is responsible for red.
Strontium.
It's an element on the periodic table. Okay? So red is because of one thing, green is because of something else, blue is because of something else. So depending on the element that's present, okay, when they get lit on fire and they explode, they're releasing energy in the form of light. So, and because they have different amounts of energy that they are releasing, okay, and that's why we see them as different colors of light.
Confusing. I liked it last show when they're word for word.
You still had problems with that.
Yeah.
This is horrible.
My
Let's see.
brain is
So-
so messed up.
Red. Red is due to the element of strontium. So if we light strontium on fire,
It'll be red. I like that color scheme. It's not
It-
red, dull fire.
It like to make greens like copper, something like that. I think. And
Stop that.
it's like
so if we were to light strontium on fire, it would burn red, and it's because it gives off a specific amount of energy.
Brewer, please report to the gym. Preston Brewer to the gym. Thank you.
Orange fireworks are due to the element of calcium. So if we burn calcium, we would see an orange flame. That's boring because most flames are orange, right?
Yeah.
Boring. Okay. Yellow is due to sodium. If we burn sodium, it's going to burn yellow. Green is due to the element of barium. So when we burn
Gold
barium,
is the fire to burn gold.
It melts.
they don't do nothing.
Like gold powder.
Nothing.
No.
a blue flame is due to the element of copper. Purple would be due to copper and strontium being burned together. Silver would be from magnesium. And white, which is basically silver when we look at fireworks, right? Burning of magnesium, aluminum, or titanium. Okay? And so it's because of the different amounts of energy that they release when they're burned. So when something is burning, it's because energy is being released from the chemical bonds that make it up. Did we talk about that with the glucose yesterday? Or was I talking about that with my biology class? Okay. So anytime we have a chemical formula, okay, some type of molecule or compound, and we break the bonds of that molecule or compound, it releases energy. And it can be, that energy can be released in a lot of different ways. In the case of the fireworks, okay, it's releasing it as heat as well as light. So if I light this candle on fire,
You gonna light it? You gonna light it?
maybe.
You should
Maybe.
light one of those in front of the gas burner, the gas deals. That'd be fun. Watch it drop that.
The candle gonna, or the thing's
No,
gonna.
it's in gas tank. And
You don't put fire in your
Oh,
bed.
no.
Oh. Heck yeah.
fire!
Oh my gosh, it's pretty old.
This little light in your mind.
That is so cool, man.
Burn some magnesium.
No chance.
No.
It solidified too quickly.
This little light. Can you see it first?
This little light of mine, I'm gonna let it shine.
Then let my fingers go.
Anyway, so right now, this is burning, right? We can all see the flame.
I can't do it.
Okay, it is breaking bonds, and it is releasing energy, and we see that energy as this flame, as light. Okay, but we can also feel that energy being released as heat, right? So I do have, I can show you how this happens with these different chemicals. Like I actually can burn these chemicals and show you guys the different colors of light.
Yeah.
I'm not gonna do it today because some of your classmates are missing. So,
It's the boring after class, you know?
so on Monday, what do we need to do?
Yeah,
Bring a lot of candles.
bring the
No, we don't need candles.
Bring a
bring
big
the
lighter.
lighter and the
Bring a blowtorch.
I can bring one.
I'll bring one.
I'll bring one.
Well, I need to show you the cathode ray tubes that I have, right? Since I forgot about it today because I was really worried about your quiz.
Yeah, they're like quick.
Okay, so we need to look at the cathode ray tubes, and we need to look at the fireworks, the burning of the chemicals.
You have to look at Katy Perry.
My favorite fireworks.
That makes me not want to show you.
What?
If you guys cannot just be quiet and listen.
Shut up.
On the bottom of page 321, it has some figures there, and it's just showing what's happening with those electrons that's causing the emission of light. Okay, the release of energy that we can see as light. So, Niels Bohr tested hydrogen because it had one electron, and so then it was easy to do. He added electrical energy to see how much energy would be released, so he added that, made the electron move, and then when he removed the energy being added to it, it moved back down in energy level, and it emitted light. Okay, so he proposed that electrons moved in circular orbits around the nucleus, and those different energy levels then, so this is our nucleus, okay, and each of these orbitals is known as an energy level. It takes a certain amount of energy level for an electron to be found there, okay? So for it to be there, it has to have a certain amount of energy. For it to be here, it has to have a certain amount of energy. For it to be here, it has to have a certain amount of energy.
Your nose makes no sense.
What?
Just read it off.
The atomic model board proposed that the electrons, say we got that, move in circular motions or
energy
What's
level.
Circular orbits.
Like it's all in the book.
Yeah, send it word for word in the
where?
It does.
Where?
Electrons
Pretty
in the
much,
Bohr
yeah.
model,
Remember
first sentence.
3A
What?
up on
Electrons
top.
in the Bohr model, first sentence.
Is that in the board model is showing where's that?
Of the Bohr, like B-A-O-R?
It's right above it.
Bohr proposed
It's
electrons
talking about Bohr right in the book. If you follow along, I am literally going in order of what's in the book, you
I
guys.
was looking at the stupid slide.
Well, I made the slideshow. I didn't make the outline or the book, but the book and the outline were made by the same company.
Oh.
So there is less energy in the electrons that live close, or don't live. The electrons that are closest to the nucleus, they will move to higher energy levels when that energy gets added. When the energy is removed from it, they release that energy and they move back to that lower energy level. And we observe that release of energy as light. So this is Bohr's model, okay? So our positively charged nucleus, these orbitals around it, we add energy into it. This electron is absorbing that energy, but it has too much energy to be contained within this first energy level, okay? Too much energy there, so it has to move out to a different energy level, okay? And so when that happens, it's absorbing that energy. But once we cut off this energy level, then that electron can move back down to an energy level that has less energy. And then the excess energy that it has gets emitted as light. We see it as different colors of light. We will see that when I show you the cathode ray tubes, because I have different gases in those cathode rays. And so you will see how the different amount of energy it releases gives us different colors. We also see that when we burn the chemicals. Okay. There were some limitations to Bohr's model. So if Bohr's model is accurate with one electron, it should apply to atoms with more electrons. However, they found that was not the case. They did find out that electrons have specific amounts of energy, but those energy levels are not arranged in specific orbits. Do you two want to be separated? Okay, then you need to pay attention. Okay, so Bohr's model looks like a solar system, right? Okay, with the sun being in the middle and the planets orbiting it. Okay? The actual model of an atom is not like that. It doesn't have that specific orbital that it takes that same path all the time. Okay? There are energy levels there, but not how Bohr said it was. It's not like a solar system. So what scientists have found is that the current model is what we call the electron cloud model. And this is on page 322. So the space that is surrounding the nucleus is known as the electron cloud, and that is where an electron is most likely to be located. It's just not going to go in a specific orbital. It can move. It still has these energy levels that are surrounding it. Think of it in a three-dimensional form. And those electrons can move around in that energy level, but they can go wherever they want in that energy level. They're not confined to a specific track that they have to follow. Okay? They're constantly moving around the nucleus, and that empty space of the atom is where the electrons are going to be found. And you're more likely to be able to locate an electron closer to the nucleus, and that's just because of the space is much smaller. So this is what our current model looks like. Does that mean it's going to stay like this forever?
No.
Maybe, maybe not. Okay, we might find more information that gives us a better picture of what the atom looks like. Okay, remember that's kind of how technology and science work. Okay, we make an advancement in science, we develop technology to get more information to advance science, right? Okay, so here in the middle, very, very small portion of the atom is made up of the nucleus. That's where your protons and your neutrons are found. And surrounding it in a cloud, and it does have those energy levels, but we say it's an electron cloud, is where your electrons are going to be found. Okay? And the very last part of these notes for this lesson is talking about quarks. And Junior did mention something about this the other day. He started saying something, but I didn't want him to quite get there yet because we hadn't gotten this far. Okay, but we can talk about it now. So, it was previously thought, so these three things, look on the board so you know what I'm talking about. Okay, protons, electrons, and neutrons are called subatomic particles. Okay, they are the three things that make up atoms, right? Okay, it was previously thought that they weren't made up of anything else, but again, advancement in technology has allowed us to find that protons and neutrons are made up of something called quarks. At this time, they don't know if electrons are made up of anything smaller than that. Electrons are also significantly smaller than what a proton and neutron is. It's like 1/1600th of the size of a proton. So, there are 6 types of protons, and you should have this wrote in your book in the margin. Up, down, top, bottom, charm, and strange are the names of the quarks.
Is the key concept.
Okay, so up, down, top, bottom, charm, and strange. Okay, and they have found that protons are made up of 2 up and 1 down quarks, and neutrons are made up of 2 down and 1 up quarks. And so I don't know where charm and strange come in. I just don't know enough about that to comment on it, honestly. Okay, so the current model can change in the future as we discover the information, as we improve on technology.
Are we doing the modern atomic model?
That was on our last slide.
Was?
Yeah.
I missed that.